Page 150, Aromatic multi-step synthesis problems. Starting with number 17. We're given several steps in a synthesis and asked to find out what's wrong with these synthesis problems. As you do these, it would be helpful for you to keep handy this table that shows the directing effects and the activation effects of various substituents on an aromatic ring. In the first example, we have benzonitrile. We're adding propanol chloride, presumably by a Friedel-Crafts acylation reaction. And notice that is positioned meta to the nitrile group, and that seems reasonable because the nitrile group is in fact a meta director. The next step involves nitration using nitric acid and sulfuric acid, and that occurs meta to the nitrile group and the ketone group. And that seems reasonable because ketones are also meta directing. So what's the problem with this? Well, the problem's in the first step. Recall that a nitrile group is a strong deactivator. That's one of the limitations of alkylations and acylation reactions, is that when you have a strong deactivator on the ring, the yields of alkylation and acylation are so small that we just say it just doesn't react. So it fails in the first step. Try B. We start with nitrobenzene. Nitrobenzene is a strong deactivator. Here's the nitro group, and it's also meta-directing. So the first step shows hydrogenation with hydrogen on nickel to reduce the nitro group to the amino group. And then we alkylate with ethyl chloride and aluminum chloride, and the amino group is in fact an ortho-para director, and therefore the ethyl group does go to the para position. It looks good, so what's wrong with this one? Well, do you recall that the amino group of all the activators, right here, it's the strongest of activators. In fact, it's such a strong activator, it's actually a Lewis base. And it reacts with aluminum chloride. And what winds up then is a nitronium cation, which becomes electron withdrawing, and any further Friedel-Crafts reaction will fail. The second reaction will not work because the amino group actually reacts with the catalyst rather than with the alkyl chloride. How about C? Start with methylbenzene. The methyl group is a weak activator. Here it is, it's ortho-para directing, and it's an activator. First step is to add this ethanol chloride group, to add a ketone, para to the methyl group. And this is a para director, so that looks good. The next step is to nitrate, and the methyl group is directing to the ortho position, so nitration would occur here, followed by reduction with hydrogen, which would reduce the nitro group to the amino group. So what's wrong with that? Well, it's all good except that the reduction would also reduce the carbonyl group to a methylene group as well, so it fails in the last step. All right, try the fourth one here. We start with chlorobenzene. Chlorine is a ortho-para director, and it's a weak deactivator. We want to add N-propyl chloride with a Friedel-Crafts alkylation reaction. In fact, chlorine is ortho-para directing, so this looks like a good site for it. There's our propyl group. The next step is to chlorinate, and again, chlorine is ortho-para directing, so chlorination can occur here. Okay, what's wrong with this thinking? There's actually two mistakes in this one. First of all, the alkyl chloride will rearrange. That's one of the limitations of alkylation. When the chloride leaves, it forms a primary carbocation, which will rearrange by a hydride shift to form a secondary carbocation. So the main product we're going to get will actually be isopropyl chloride. N-propyl chloride would be a small component, a small percentage. The second problem is once the alkyl group is added, whether it be isopropyl or N-propyl, it's an activator. The chlorine is a deactivator, so the next substitution is determined by the activator, and that would be ortho to the alkyl group, not ortho to the chlorine group. Two problems there. it says that the fourth reaction is possible, and we're asked to propose a route for it. So let's try that. We'll start with chlorobenzene. Recall it's an orthopara director. We do want to add an alkyl group and propyl group para to it. So how do we do that? Do you recall that if you use the acid chloride form, that will not rearrange, and that will add to the para position without rearrangement. So the next step, we want to chlorinate the ortho position, that is ortho to the chlorine, and that's going to work because chlorine's an ortho director, and this carbonyl group is also meta to itself directing, so no issue there. We'll chlorinate next. That's chlorine with the catalyst FeCl3. And the last step then, we can hydrogenate on any of the catalysts, nickel, palladium, platinum, and reduce the carbonyl group that's in the benzylic position. Here it is, in the benzylic position, it'll be reduced to a methylene group. So we can get our final product, which would be 1,2-di-chloro-4-propyl-benzene. Aromatic reactions, page 151. Here we have toluene. We want to be able to convert that into 2-bromo-4-nitro-benzoic acid. As a point of interest, the carboxylic acid group has the highest priority in terms of naming, so that by default will be carbon 1, 2, 3, and 4, and hence the name 2-bromo-4-nitro-benzoic acid. In any case, how are we going to do this? Now, the methyl group can be oxidized at any time to the carboxylic acid group. And they're different. The methyl group is activating and orthopara directing, ortho and para, whereas the carboxylic acid group is deactivating and meta-directing. But notice that the bromine and the nitro group are ortho and para to the methyl group, so that looks like we should do those first and do the oxidation last. Let's nitrate first. I believe you could brominate first if you wish. How do we nitrate? Sulfuric acid and nitric acid mixture will nitrate the aromatic ring. Now, where's that going to occur? Well, the methyl group is ortho-para directing, so one of the major products will be para to the methyl group. So now we have para-nitrotoluene. We next want to brominate. We want to brominate the ring. We'll use bromine, liquid bromine, and FeBr3 catalyst. So since the methyl group is orthopara directing, we'll get a major product with the bromine ortho to the methyl group. And then the last step is simply the oxidation of our benzylic carbon, this methyl group, to a carboxylic acid. And that's done with potassium permanganate in acidic solution at some reasonably high temperature. Take a look at the next question. Here we want to convert benzene into this compound. I would call that 1-bromo-4-vinyl benzene. That's one possible name. If we named this as styrene, we could say parabromostyrene. In any case, how do we do it? We need to brominate, and we'll need to add this 2-carbon vinyl group. Now, do you recall that you cannot alkylate with an aryl chloride, nor can you alkylate with a vinyl chloride? So we can't directly add vinyl chloride to this. We can't directly add a vinyl group. We'll have to add the 2 carbons and then convert it later. So let's start with the alkyl group first. We'll put 2 carbons on it. So we'll use Friedel-Crafts alkylation with the Friedel-Crafts catalyst, and we'll get ethylbenzene. Now that's ortho-para-directing. It's an activator. We should have no problem with brominating into the para position. So we'll use bromine and the bromine catalyst FeBr3. That will be para to the alkyl group. Now how do we convert the alkyl group, the ethyl group, to the vinyl group? Well, we can do it, if you recall, we can use N-bromo-6-enamide and benzoyl peroxide. And that will brominate the benzylic carbon right here. It won't brominate the ring. If you want to brominate the ring, use bromine and FeBr3. If you want to brominate the benzylic position, use NBS and benzoyl peroxide. Let me put some carbons in here. And then how do we convert that to vinyl group? We can do a dehydrohalogenation minus HBr using KOH in ethanol. This is a secondary alkyl halide right here, and so it'll undergo an elimination reaction. Bear in mind there are no hydrogens on this carbon, so we don't have to worry about competing reactions. We'll get our product, 1-bromo-4-vinylbenzene. So our next problem asks us to convert benzene to this compound. Now, what is that anyway? Well, it's not something you're responsible for at this point, but it's an alcohol. That's the major functional group. So it's ethanol with this substituent on it. So for sake of interest, I would call this 2, and the substituent be 4-bromo-phenyl ethanol. In any case, regardless of the name, how do we do that? Well, I'll let you stew on it for a while, but when you've had enough, follow with me here. The easiest way would be to take our product from the previous reaction, which is almost there, take our bromo-vinyl benzene, and simply hydrate it. Now the trick is we want the hydroxyl group in the anti-Markovnikov position. Right? So how do we do that? Recall that we can use borane gas in tetrahydrofuran solvent, followed by sodium hydroxide and hydrogen peroxide. And this gives us the anti-Markovnikov alcohol, which is our product in this case. The last question on this page asks us to convert benzene into this product, whose name would be. Well, I'd be inclined to call this aniline, and therefore this carbon is 1, 2, 3, 4. So I would name that 2-iodo 4-methyl aniline. And there's other possible names for that as well, but let's focus on how we're going to do this. Now just bear in mind that the amino group is a strong activator. It's ortho-para-directing, but you can't alkylate. Recall, it reacts with the aluminum chloride. So we can't have the amino group on and then try and alkylate. It won't work. Nor could we have the nitro group on first, because it would be meta-directing, not para-directing. So it looks to me like we've got to put the alkyl group on first, and then we'll go from there. As a first step, then, let's alkylate this ring. Methyl chloride, aluminum chloride catalyst, Friedel-Crafts alkylation reaction, gives us toluene. This methyl group is activating and ortho-para-directing. If we iodinate now, we're going to get iodine ortho or para to the methyl group. That's not going to work. What can we do next, though? We want the nitrogen group para, so let's put that on next. That'll have to go on by nitration. Conc nitric, conc sulfuric. Now we have para-nitrotoluene. We're getting close. Now we want to iodinate. Still not a good time, though, because the iodine would be ortho to the methyl group rather than to the nitro group. But if we, at this time, reduce the nitro group to the amino group, hydrogen on nickel, we convert our nitro group to the amino group. And this is a strong activator. And it'll direct preferentially ortho to itself. And now would be the time to iodinate. Now how do we do that? We have iodine, but we need a promoter like copper 2 chloride or hydrogen peroxide. And that should do it. Page 152. Problem D, we're asked to convert benzene into this monster. What would be the name of that? Well, I'm going to name that as a benzene sulfonic acid, and that determines that carbon to be the number 1 carbon. So we would have then 4-chloro. 2, do you recognize this group? That's isobutyl. Benzene sulfonic acid. The only space is between the ic and the acid. Otherwise, it's one word. In any case, how are we going to do this? Well, one of the things you want to consider is this isobutyl group. It will have a primary carbocation. If you were to do this by alkylation with a chloride attached here, it would produce a primary carbocation which would definitely rearrange, and this would not be a major product. That's a pretty good starting clue, and it tells you this really has to be added as an acyl group. It can be reduced later. So as an acyl group, there'll be a carbonyl here, and thus it would be meta-directing, and that looks like chlorine could be added after the acyl group. Now the sulfonic acid group requires the addition of oleum, fuming sulfuric acid, and sulfur trioxide. Now that's ortho to this alkyl group. So it looks to me like if we reduced the carbonyl group to the alkyl group, it's then ortho directing, and we can sulfonate in the last step. And that seems like a good plan here. So let's start by acylation. We'll add this acyl group with the Friedel-Crafts catalyst. And that will give us the carbonyl group on the ring. And that group, as we said before, is electron withdrawing and meta-directing. So this is a perfect time then to chlorinate. How do you chlorinate the ring? Use chlorine and FeCl3. And here's our chlorine meta to this meta-directing group. At this point we could reduce the acyl group using hydrogen on nickel, palladium, platinum, etc. Recall that this reduction catalyst will not reduce the unsaturation in the ring. But it will reduce carbonyls to methylene groups. The carbonyl group in the benzylic position is particularly susceptible to reduction. And then at this point we can sulfonate. Because our alkyl group is orthopair-directing, we'd use oleum, which is fuming sulfuric acid. It's a mixture of conch, H2SO4, saturated with sulfur trioxide gas. Our next problem asks us to convert benzene to this alkene. If I had to name this, alkene likely has precedence. I'd number this 1, 2, 3. This would be 1-phenyl propene. Notice also the stereochemistry. We have hydrogens on opposite sides, or larger priority groups on opposite sides. So this has to be trans 1-phenyl propene. And that should ring some bells. How do we make a transalkene? Do you recall that a transalkene is made from partial reduction of an alkyne with sodium and liquid ammonia? That would be really helpful to remember that. So we work backwards as well as forwards. So that was sodium in liquid ammonia. So then how do we get from benzene to this alkyne? We have to add some carbons, and we'll have to add some unsaturation. Well, let's add some carbons. We need 3 carbons here. And once again, we can't add it by alkylation because these 3 carbons are sequential and they'll rearrange to an isopropyl group. So let's add these as an acid chloride. Friedel-Crafts acylation. All right, and then we're going to have to reduce this. We can reduce it with hydrogen on nickel, palladium, platinum. How do we go from this propyl group to this 3-carbon alkyne? We need some functionality in here. Our next step would be to add N-bromosuccinimide and benzoyl peroxide. And why is that? Well, that will brominate the benzylic position just once right there, and that will give us some functionality to work with here. Now we can use KOH in ethanol, and then we'll eliminate hydrogen bromide, giving us an alkene. That alkyl halide is a secondary alkyl halide, so that'll undergo elimination with a strong base. And then go from the 3-carbon alkene to the 3-carbon alkyne. We've done that a few times. We're going to halogenate. I'll use bromine in dichloromethane. And finally, we can do a double dehydrohalogenation. 2 moles of KOH, triethylene glycol, high temperature solvent, 200 degrees C, minus 2 HBr gives us our alkyne. When I mark these, there's usually a mark for each set of reagents and 2 marks for intermediate products. It'll be marked like this. That's a lot of steps. Our next problem asks us to convert benzene to this aniline compound. If I say it's aniline, carbon 1 is designated. The carbon attached to the amino group, this would be 3-ethyl aniline. How are we going to do that? Notice that the amino group is meta to the alkyl group. Now the amino group is an ortho-para-director, so that's not going to work, and the alkyl group is an ortho-para-director, so we need some meta-directing capability. If we were to add the nitro group on first, it is meta-directing, but it's so strongly electron withdrawing that we could not alkylate or acylate. So I think we're forced to start with the alkylation first. But if we add it as Friedel-Crafts alkylation, we have the alkyl group, which is not meta-directing. However, if we add it as an acyl group, we solve our problem. So there's ethanol chloride with aluminum chloride catalyst. There's our ketone. Now that is meta-directing, so we could now nitrate to the meta position. How do we nitrate? Well, conc nitric acid, conc sulfuric acid. Produces nitronium ion, a very powerful electrophile. All right, so we have our groups in the right places. The final step then is simply to reduce with hydrogen, nickel, palladium, platinum, and both the carbonyl in the benzylic position and the nitro group will both be reduced simultaneously to our product. So the last problem on this page asks us to convert benzene into this phenolic compound. Now how would you name this? If I say it's phenol, then this is carbon 1, 2, 3. So how would we name the substituent? Well, how about phenylmethyl? That might work. So we'll say it's 3 phenylmethyl, and we'll put that in parentheses because it's a complex substituent, phenol. Now the phenylmethyl group is sometimes called a benzyl group, so possibly there are other names for that, but let's focus on the task at hand here. How are we going to put the hydroxyl group and the benzyl group on the same ring? Well, first of all, remember that you can't put a hydroxyl on directly. It's a two-step process. First we have to sulfonate the ring and then carry out alkali fusion with molten sodium hydroxide at 300 degrees Celsius, followed by some acid. So with the hydroxyl group on, well, it's ortho-para-directing, so we can't add the alkyl group afterwards. If we put the nitro group on first, it's meta-directing, but you can't alkylate or acylate because the nitro group is deactivating. So let's add this carbon group on first. Now we could add it by alkylation or acylation, but considering that we want the next group to go on meta to it, we should add it as an acyl group so we can take advantage of that. So let's add benzoyl chloride with the Friedel-Crafts catalyst. Now this is meta-directing, so we want to sulfonate next with oleum, which is fuming sulfuric acid, conc sulfuric acid with sulfur tetroxide gas dissolved in it. So our next step would be to reduce the carbonyl with hydrogen on nickel. Recall that the benzylic carbonyl is particularly susceptible to reduction. And then finally we can carry out alkali fusion. This is a two-step process. Molten sodium hydroxide at 300 degrees Celsius, ouch, followed by some hydronium ion to reprotonate the phenoxide. Are you wondering perhaps, could we have done the alkali fusion first and then the reduction? Well, maybe, but be careful. Recall that the severity of this alkylation reaction is such that it says only alkyl groups will survive. I'm not sure about the fate of the carbonyl under those conditions, so it's safest to go reduction first to an alkyl group and then carry out the alkali fusion. On page 153 we have a few more problems. Here we have toluene. We're asked to convert it to this aromatic alkyne. So how are we going to do that? It looks pretty daunting, doesn't it? Well, you work on it for a bit and then I'll show you a shortcut to what you might be thinking. So perhaps not what you were thinking, but why not brominate this toluene and make it an alkyl halide? You'll see what I mean. We want to brominate with N-bromosuccinimide and benzoyl peroxide. And that will brominate the benzylic position just once. We have CH2Br, a bromomethyl group. So why not treat this as if it's a primary alkyl halide, which it is, and let's think about perhaps adding all of this as an alkynide in an alkylation reaction. Tricksy, yes? So let's say we react it with some sodium salt of an alkynide. See, nothing says we can't. It's an open question. So this alkynide is a strong base, good nucleophile, and it will undergo a substitution reaction with a primary alkyl halide. And just that quickly we have our product. That's a lot easier than building everything from scratch there. Interesting. So problem 19 says using benzene and methyl chloride as the only carbon-containing reagents, draw a reaction sequence from benzene to diphenyl methane, and there should be no space there. That's one word. Let's draw the starting material and the product and see what we have to do. Well, benzene going to diphenyl methane. Well, methane is just one carbon. It's disubstituted with two phenyl groups. There's diphenyl methane. But remember, we're only allowed to use benzene and methyl chloride as our reagents, so I'm thinking we better go ahead and add a methyl group to the benzene since we're pretty restricted with what we can do. So let's add methyl chloride with the Friedel-Crafts alkylation catalyst. There it is. So it's looking a little closer. How can we add the aromatic ring to this methyl group? Right now our methyl group has no functionality. It's just a saturated hydrocarbon. But remember, we can add a bromine to the benzylic carbon by NBS and benzoyl peroxide. Very useful reaction. Substitution reaction CH2Br, methyl bromide. This has functionality. So we can use this as our alkyl group as if it was a chlorine. And we use the Friedel-Crafts catalyst AlCl3. What happens here is the bromine leaves, if you will, to bond to the aluminum, just like chlorine would, forming a carbocation, a benzyl carbocation. And so then we can react this with benzene in a Friedel-Crafts alkylation reaction. Tricksy again. That should work. So last one, number 20. Using benzene and ethyl chloride as the only carbon-containing reagents, draw a reaction sequence from benzene to 1,2-diphenylethane. Let's draw this out and see what we're looking at here. Benzene. Now, diphenylethane. Similar to the last problem. This time we can use benzene and ethyl chloride. Well, let's start by adding the ethyl group to the benzene in a Friedel-Crafts alkylation reaction that builds some of the structure that we're looking for. That would be ethyl chloride, Friedel-Crafts catalyst, okay. There's ethyl benzene. Looks pretty close. Now how are we going to add the aromatic ring to that carbon on the end right here? Well, like before, let's give it some functionality. Let's use N-bromosuccinimide and benzoyl peroxide. And what happens then? We brominate the benzylic carbon. It's not exactly where we want. We'd like to have that bromine on the end carbon. Can we move it over? Well, what if we carried out a dehydrohalogenation with KOH and ethanol? And that would give us an alkene. Is there a way we can move a functional group to the end carbon? Or what about if we brominated in the anti-Markovnikov position? We could do that with, say, bromine and hydrogen peroxide. That gives us the bromine where we want it. Okay, so now we have bromine out here. So now we have functionality on the end carbon. Can we then react that with benzene? Let's give it a try. Say we take benzene. Now think of the alkyl bromide as if it was an alkyl chloride, like RCl in a Friedel-Crafts alkylation reaction. Treat it the same way. So assuming that the bromine leaves with the catalyst, let's write some catalyst in here, AlCl3, and the bromine leaves here, we'll have a primary carbocation. And that carbocation can then bond with the aromatic ring, and we'll get some of our product. We'll get some of, well, that product, right? But because it's a primary carbocation, we do have a problem. That's going to rearrange by a hydride shift, and we'll get some carbocation here. And so in fact the major product will have this structure. Not quite what we're looking for. This in fact would be 1,1-diphenyl ethane instead of 1,2-diphenylethane. And that would be our major product. The product we're looking for is actually a minor product. So we have a problem here that we really can't solve in the first semester. But if you're around in the next organic course, you'll learn some new reactions in which you can carry out the task we just faced. And that's it for aromatic multi-step synthesis problems.